We frequently encounter numbers in everyday life. Let's look into some of the situations that arise in our lives, generate the sequences of numbers they involve, and check the patterns, if any, we can find in those numbers. For example, let's say that 500 rands is deposited in a bank which pays compound interest at the rate of 10% annually. The amount in the account at the end of each year for the next 10 years will be as shown. Here's another situation. The number of bacteria in a culture doubles every hour. If there were 30 bacteria initially, then the numbers of bacteria present at the end of every hour until the nth hour are as shown. In the third situation, a company calculates the annual depreciation for a machine at the rate of 20%. If the present worth of the machine is 15,625 rands, then the worth of the machine at the end of each year will be given by the sequence of numbers shown. Let's now analyze the patterns followed by the sequence of numbers in each situation. In a sequence corresponding to each situation, observe that each term after the first term is in a constant ratio with the preceding term. Such special sequences whose consecutive terms are in constant ratio are known as geometric sequences or geometric progressions. Let's look further into geometric progression. In the following geometric sequences, we have observed that each term is in constant ratio with the previous term. The constant ratio is known as the common ratio. This common ratio can take any negative or positive value, but cannot take the value 0. As a result, we have increasing and decreasing geometric sequences respectively. Further, each of these geometric sequences can be written with respect to the first term and the common ratio as shown. In general, if the first term is A and the common ratio is R, then we can write the terms in a geometric sequence as shown. Here A and the common ratio R can take any value other than 0. These terms are non-zero because division by 0 is not defined. In fact, precisely for this reason, none of the terms of a GP can be 0. A geometric sequence is categorized as increasing if the common ratio R is greater than 1, decreasing if R is less than 1, or constant if R is equal to 1. A geometric sequence may also be finite or infinite depending on whether the number of terms in the sequence is finite or infinite. Note that a geometric sequence advances in a definite pattern. Hence, the geometric sequence is called geometric progression or GP. The ancient Greeks called the geometric progression geometric. The reason for this may be that it is often used in geometry and obtained by multiplying the first term by increasing powers of the common ratio. Let's explore how geometric progression looks when plotted graphically. Consider a geometric progression representing the depreciation value of a machine as shown. It has a common ratio equal to 0.8 and the number of terms n equals 8 as shown. Label the number of terms on the x-axis and the corresponding terms on the y-axis. Now, plot a term against its corresponding term number as shown. Observe that we get an exponential curve for geometric progression. Here, the common ratio is less than 1 and hence the shape of the graph is a falling curve. Similarly, when the graph is plotted for the geometric progression corresponding to the number of bacteria at the end of every hour, then we get a rising curve as shown. Here, the common ratio is greater than 1 and hence the rising curve. Hence, our discussion and observation can be summed up as shown. Let's consider a geometric progression with terms A1, A2, A3 and so on up to AN. Let the first term A1 of a GP be A and let the common ratio be R. As we know, in a geometric progression, each term except the first term is obtained by multiplying the common ratio by the previous term. Therefore, by definition of GP, we have A1 equal to A. Similarly, by definition, the second term A2 is obtained by multiplying the common ratio R by the previous term, that is the first term A1. As a result, the second term is AR. Likewise, the third term, fourth term and so on can be obtained as shown. Observe closely the number of the term and the index of R. Note that the index of R is equal to 1 less than the number of the term. For example, for the first term A1, the index of R is 0. In the second term A2, the index of R is 1. In the third term A3, the index of R is 2, and so on. Thus, the nth term of an arithmetic progression is equal to A R to the power of n minus 1. In fact, the nth term is known as the general term of a geometric progression. Now, can you generate a GP if its first term is 2 over 3 and the common ratio is 1 over 3? Let's find out. We know that the nth term of a GP is its general term. Substituting A and R, we get equation 1. Now, substitute n with 1, 2, 3, 4 and so on. As a result, we generate a GP with the first term 2 over 3 and the common ratio 1 over 3 as shown. Now find the nth term of the given geometric progression. In the given GP, the first term A equals minus 2 over 3 and the common ratio R equals 9 as shown. Let AN be the nth term of the given GP. We know that the nth term of a GP is given by the general term as shown. Label this equation 1. In equation 1, substitute A with minus 2 over 3 and R with 9 as shown. Simplify equation 2 to get the general or nth term of the GP. Let's study some properties of geometric progression. Consider a GP as shown. It has the common ratio R equal to 2. Label this GP as 1. Now, multiply 3 to each term of the GP denoted as 1. We get a sequence labeled as 2 as shown. Note that the resulting sequence 2 is a GP with the common ratio 2. Hence, if a constant is multiplied to each term of a GP, the resulting sequence is also a GP. Now consider two geometric progressions such that in the first GP, common ratio is 2 and in the second GP, the common ratio is 3. Label these geometric progressions as 3 and 4. Multiply the two geometric progressions 3 and 4 to get the sequence 5 as shown. Note that the resulting sequence 5 is also a GP with the common ratio 6, which is the product of common ratios 2 and 3. Hence, if two geometric progressions of common ratios R1 and R2 are multiplied together, then we get a geometric progression with a common ratio R1-R2, which is the product of R1 and R2. Hence, the properties of a GP can be summarized as shown. Consider a GP as shown. Now, to every GP, there is a corresponding series which is obtained by adding the terms of the geometric progression. If there's a finite GP of n terms, then let's find the sum of the n terms in the GP. Denote the sum of n terms of the GP by Sn such that it is given by equation 1 as shown. Now multiply both sides of equation 1 by r. We get equation 2. Now subtract equation 2 from equation 1 such that we get equation 3 as shown. On simplifying, we get equation 3 as shown. In fact, equation 3 gives the sum of n terms of a GP. Equation 3 can be expressed in two ways depending on the value of r. Equation 3 also gives the sum of n terms in the GP for r less than 1. However, if r is greater than 1, then the sum can be modified as given by equation 4. While if r equals 1, then equation 3 is not defined. Since the sequence is constant with all terms equal to a, the sum is given by equation 5 as shown. Hence, depending upon the common ratio r, the sum of n terms in a GP can be evaluated using the formulae as shown.